I agree.
We have a question.
I've got a question over there.
Oh yeah, question's it. Thanks for reminding me. I do.
I always
Here we go.
feel like that was all.
I gotta get into that habit. I research it in the morning and then I forget about it. So here's the question. You have 2 minutes. Go. This is in the non-calculator section of the exam too. So no calculator allowed for this question. One more minute. All right, anybody have a guess? What do you think? Does anybody else think it's C? Does anybody else have another answer?
I said D.
I said D too, because the
That's
exponent,
executed this.
Okay, let's come back to that. Why do you think it's D? Yeah.
because when working with limits at infinity, the bottom is less than the top limits.
That's true for rational functions. If it's a rational function and the order of the top is bigger than the order of the bottom, then the limit's infinity. So like, for example, if I had something like the limit as x goes to infinity of 5x squared minus 2x plus 1 over x plus 2 or something like that, right? You look at the order of the top and the order of the bottom. If the order of the bottom is bigger, then the answer is 0, right? This limit is 0. If the orders are equal, like if this was x squared and this was x squared, it would be the fraction of leading coefficients. This would be like 5 over 1. If the order of the top is bigger, then the answer is either plus or minus infinity. It's infinite. But the reason why that's true is relative rate of growth, right? The top of this fraction is growing at a faster rate than the bottom of the fraction. And if you have a fraction in which the top is growing faster than the bottom, then that fraction is going to be approaching infinity. If you have a fraction in which the bottom is growing faster than the top, then that fraction is approaching 0. The answer is actually C. Why do you think the answer is C?
For that reason.
For that reason, right? Because if you look at this function, it's an exponential function. It's growing much faster than any polynomial function, right? If you look at like order of growth, right? Like orders of magnitude, exponentials are like the biggest functions, the fastest. They grow the fastest, right? After that, it's polynomials. And after that, it's logarithmic, right? These are all increasing functions. Exponentials look like that. Polynomials also look like that, but at a slower rate. And logarithms look like that. They're actually slowing down in their growth as you get bigger.
So what's the limit of D then?
Okay, so if you look at D, I think the answer would be 3 over 2. Because the polynomial part of this function, like if you take 3e to the x plus x cubed over 2e to the x plus x squared, if you substitute in a huge number, like 1,000,000, this number far outweighs and dominates the x cubed. And this part of it far outweighs and dominates the x squared. So even though x cubed is bigger than x squared, in comparison to the exponential function, they're tiny, they're insignificant, they're totally dominated. The answer is 3/2 for that function. If you look at the other ones, like the first one is kind of the same thing. The x squareds dominate those polynomials or those functions. So this answer would be 1, right? 1/1. The second function would be 0, definitely because the order of the bottom would be bigger. The third one, like I said, I think is infinite. The part D, choice D would be 3/2. And what do you think choice E would be? Nope.
I said 1.
Nope. Nope. You can think of this part E as being, if I take ln 3x or ln 2x, I could rewrite the top as ln 3 times ln x, and I could rewrite the bottom as ln 2, plus ln x. Who said 1? I think it's 1. Because the ln 3 is just really, really tiny compared to the ln x when you plug in really large numbers. Right? These are laws of logarithms. You can rewrite this as that, and you can rewrite that as that. I think the answer is 1. Yeah, I think it's 1. Any questions? So you're looking, when you're taking the limit as x goes to infinity, yes, if it's a rational function, you look at powers of x, but more importantly, you're looking at like how fast is it growing? Orders of magnitude, which one's the largest for big numbers? Okay, that's what you're looking for. Okay. So yesterday, we did indefinite integrals with u substitution. Is that pretty easy? Any questions about that stuff? Remember, there's like 2 ways to go about it. You can do the normal u substitution, change everything back into x's at the end, and then just plug in the numbers and subtract them. Or you could do u substitution, but then change the limits of integration by using your definition of u, change the x's into u's. And then you don't have to change back into x's. So there's benefit of doing it that way, but they're going to make sure you know how to do it both ways. So you should be able to do it both ways. Okay, so today we're going to talk about integrals and area. So this is a topic that we're going to spend a lot more time on when we get to, I think it's unit 8. It's the last, I think it's in the last unit. It might be in unit 7, but anyway, we're going to spend a lot more time on it, but we're just going to scratch the surface today. This is actually one of the most important applications of integrals that there are. And here's the idea. Here's the fact. The fact is, a definite integral of function f of x over an interval of xi's to b is the signed area between f of x and the x-axis. Okay, so this term signed area is a little bit weird, but all that means is if the area happens to be above the x-axis, then it comes out to be positive, and if it happens to be below the x-axis, then it turns out to be negative. Okay, that's what signed area means. So the picture would be like this: if I have a function and kind of looks like this, whatever, f of x, and this is a, this is b. Then the area of this weird shaped region, which isn't really anything we can find using real, like, normal geometry formulas or anything, that area is actually equal to the definite integral from a to b. F of x dx. That's a great question, and we'll talk about that more in this unit, actually, about why that is the way it is. But before we explain why it is, I'm just going to do some like really simple problems involving it. That's a great question, though, and I don't blame you for wondering why that's true. Because if you think about it, it's like, okay, so the derivative is the slope of the tangent line, but the integral, which is just the opposite of the derivative, is an area. It seems a little like a stretch, but all right. So we'll talk about why it is later. What? It kind of makes it's sort of like the three-dimensional equivalent of the slope of the tangent line, kind of, maybe. I don't know. All right. And then likewise, if I have a function that's below the x-axis, so say you have a function like this or whatever, f of x, here's a, here's b, and that area this area is just going to end up being the negative of the integral from a to b. F of x dx. So, for example, like they could give us a problem where we had a simple function. Let me use graph paper. You want to borrow some or take some that's on the back shelf there. Or you can just sketch it. I don't really care. It appears as if the gallery is not loading.
Yep.
All right, plan B, just a sketch. So suppose I have a simple piecewise linear function. Okay, so suppose this piecewise linear function looks like this. So this point, negative 1, 1. Okay, and then it goes across there. And down to here. And then like that. So suppose that's f of x. I'll give you a second to copy it down. So points look like where they are, and they actually are. So this point is actually at negative 1, 1. This point is at 1, 1. This point is at 2, negative 1. And everything else is just where. So suppose we wanted to find the definite integral from -2 to 3 of f of x dx. So all we would have to do is just geometrically find these areas. Like, I would just need to find this area as a positive area. That's just a trapezoid, right? So I could calculate its area, no problem. Or I could think of it as two triangles and a rectangle. That would be even quicker, right? Like, I'm just thinking I could split it like this and say this area right here is definitely 2. That's easy to just count squares, right? This area is definitely 1/2. And this area is actually 1/4, right? It's 1/2 of base times height, half of a half times 1. So this is 0.25. I'm trying to do this the quickest way I can, which is just counting squares. I could do the trapezoid formula. I could say 1/2 of h times b1 plus b2. Could do that. And I'd get the same answer for the total area. And then I could calculate this area right here. Same thing. I would probably just split it up into two triangles. That seems like a quicker way to do it than doing 1/2 base times height, where the base is a weird, like 1.5. That seems a little harder to me for some reason, but maybe it's not. This is 0.5, and this is 0.25. And then remember, all the green stuff here is going to count as positive area, and all of the blue stuff is going to count as negative area. So essentially, you got this triangle, which cancels, in effect, with this triangle. That's going to be a positive 0.5. This is going to be a negative 0.5. Same thing here. This is a positive 0.5 or 0.25. This is a negative 0.25. They cancel each other out. The answer is 2. Does that make sense? Or what if I had a problem that was like the integral from negative pi to positive pi of sine x? Just picture sine x. Rather than actually evaluating this definite integral, I'm just going to picture sine x. Sine x looks like this. There's negative pi. The answer is going to be 0, 100%, because you're going to have this stuff here, which has the exact same size and shape as this stuff here, but one of them counts as a positive area, one of them counts as a negative area, so the answer is just going to be 0. They're going to cancel each other out. How about this? What if I have another piecewise function? This time, let's suppose it's not piecewise linear, but it has like other stuff happening. So suppose I have this function, which is actually a semicircle, like that. Semicircle. And let's say this one is, well, that's it. And let's say I want to find the integral, so this is f of x. And I want to find the integral from -2 to 3. What can I do? Yeah, I could just take half the area of this circle, right? 1/2 pi r squared. So this is 1/2 of pi times 2 squared. Okay. And then the little triangle, this is, let's just say that goes up to 1. That's this segment has, or this ray has a slope of 1. So this would be like 0.5. Done. That's the integral. That's the value of the integral. Now, there's other ways we could do this. We could actually evaluate the definite integral analytically. Like, we know that this curve right here is really x squared plus y squared equals 2 squared, 4. So this upper semicircle is really just y equals the square root of 4 minus x squared. Right? And I know this line right here, it's a line of slope 1. If I had continued to draw out with slope 1, it would cross through the y-axis at -2. So this line right here is y equals x minus 2. Does everyone agree? And so I could have just done the integral from -2 to +2 of the square root of 4 minus x squared dx, which incidentally, I don't know how to integrate that, right? Neither do you, because it's not a u substitution problem or anything like that. Plus the integral from 2 to 3 of x minus 2 dx. I could have just done this though on my calculator and gotten an answer. Let's check it just to make sure. If I take math 9, the integral from -2 to +2 of the square root of 4 minus x squared dx plus math 9, the integral from 2 to 3 of x minus 2 dx. Get a little decimal answer, right? If I did the actual stuff I did here, which is 1/2 pi r squared, which simplifies to really just be 2 pi. If I take 2 pi plus 1/2, I get the same answer, right? And again, the reason why they get slightly different answers, like towards the end they differ a little bit, is because of the way that your calculator calculates definite integrals. But we're rounding to 3 decimal places, so these answers are equivalent to 3 decimal places. Okay? What about this? What if I have, sometimes they'll give you a problem where instead of you being able to calculate areas using geometry, they might just tell you areas of weird shapes. Like, for example, they might say, here's a function, and it looks like this. Okay? And they might say, this x value is -9, and this x value right here is 7. And then they might just assign areas. Like they might say, this area of this little hump right here is 11. And this area right here is 2. This area right here is 2. Okay. And this area right here is 14. And they might say something like, find the integral from 7 to -9 of f of x. What are they trying to trick you with here?
So be -1.
Yeah, they're switching the limits of integration on you, right? Normally, you go from like the small number to the large number, but this is really just going to be the integral, or negative the integral from -9 to 7 of f of x dx. And then it's just adding up and subtracting areas. This is going to be the negative of 11 minus 2 plus 14. So this is 25 minus 2 is 23, so this is -23. Make sense? So the Delta Math assignment tonight, it's just these types of problems. They're either going to give you a piecewise function that you can calculate areas like using geometry formulas, Or they're gonna give you a problem like this where they actually just tell you what the areas are and you have to add and subtract. But they're kind of easy problems, don't you think? So I just encourage you, if it's a piecewise function, like do it in the quickest, easiest way you can, okay? Trapezoids, I think, are almost always easier to calculate their area if you just take them as triangles and rectangles. It's much easier to do it that way, especially if it's on graph paper. Triangles, sometimes it's easier to split it up into two triangles, okay? You get the answer quicker. And then circles and stuff like that, you have to use the pi_r² formula, but they'll either be quarter circles or half circles. They're not going to be anything weird, but just a random arc. Any questions? Okay, I'm going to stop recording, but the homework is on Delta Math, and it's just called integrals and area. Okay.